Welcome to the presentation of my doctoral thesis, titled Compositional Verification of Rich Program Properties in Separation Logic. First, a few words about the setting. In this work, we're interested in automatic deductive verification of heap transforming programs. Input programs are written in a statically typed, object-oriented language. The programmer needs to implement each method that comprises the program and also needs to specify each of these methods using preconditions and postconditions. We're interested in reasoning about one method at a time. For example, if the method attach is already formally verified, then in order to reason about its client, we don't need to know its implementation details. In fact, the implementation of attach could be part of a library for which the source code is not even available. In this sense, our setting is modular. To support modularity, we build on top of separation logic, which is a prominent framework for modular reasoning. In separation logic, each method operates within a limited fragment of the heap, and this is called this method's footprint. We're interested in a verification that can be automated, since real-world programs these days tend to be huge and highly complex. It takes an expert to verify them, and even for experts, the process is time-consuming and it doesn't scale unless it can be automated. Fortunately, there exist powerful tools for automating reasoning in separation logic. Here are the main questions that arise while reasoning about the method call in our setting. First, how can we satisfy the precondition of the callee? And then how can we use the information in the callee's postcondition and propagate it back to the client? In separation logic, also an intermediate question arises, namely, what are the properties that are not affected by the call? This is called separation logic framing, and I will explain this next in more detail. For that purpose, let's zoom in onto this method call, and since we're dealing with heap transforming programs, let us assume that we have some initial heap configuration in the pre-state of the call. The pink box here denotes the client's footprint, and the gray circles are heap objects, while the arrows represent references between them. The first step in reasoning involves splitting the client footprint into two disjoint parts, namely the footprint of the call and the remainder heap fragment, which is called the. What's interesting about the frame is that the heap configuration in it does not change as a result of the call. Conversely, the heap configuration in the footprint changes as specified in the postcondition of the callee. The final step involves joining these two disjoint heap fragments while propagating the information from the footprint back to the client. While reasoning about a method call involves two program states, we can see here that we have to solve instances of the same general problem. This is the problem of compositional reasoning. Namely, how can we, given the properties of a larger heap fragment, represent these using a combination of similar properties of its disjoint subparts? In my thesis, I consider two categories of rich program properties. The first category summarizes the data stored in data structures. For example, if we consider a graph marking algorithm, then one interesting property would be the number of marked nodes. And the number of marked nodes within the client footprint is equal simply to the sum of the numbers of marked nodes in the footprint and the frame of the call. The simplicity of this representation is due to the fact that data summary related properties are naturally compositional. The second category of properties that I consider in my thesis is related to the shape of the structure. Unlike data summaries, shape-related structures are non-compositional in general. For example, it is sometimes interesting to verify that the structure remains acyclic after a method call. However, even if two disjoint heap parts contain acyclic structures in them, their union may still have a cycle. This shows that reasoning about shape-related properties in a compositional setting is fundamentally challenging. Next, I will explain how the contributions of my thesis address some of the challenges of compositional reasoning. The first technical contribution is a technique for reasoning about data structure comprehensions, which are a form of data summaries. I will introduce comprehensions shortly, but the novelty of this technique is that it enables modular reasoning while supporting arbitrary heap structures, whereas in prior work only structures with totally ordered nodes were supported. The second technical contribution is a technique for reasoning about shape-defining local reachability properties. I will introduce local reachability later on in the talk, but the main novelty of this technique is that it again supports modular reasoning while significantly generalizing the supported structures. For example, this technique supports arbitrary directed acyclic graphs. The third contribution is a verification debugging technique. This technique aids the programmer in authoring formally verified software, especially in our setting. All of the techniques presented in the thesis are based on separation logic, and this allows them to benefit from the existing tools and techniques that also target separation logic. In particular, all the techniques in the thesis are fully intercompatible. Beyond the scope of the thesis, I've also contributed on the level of tool integration in the course of my PhD studies. In particular, Viper IDE is a verification-oriented IDE for the Viper intermediate language. It's implemented in a modular way, and its components are also used by other projects that target the Viper platform. Last but not least, I've also contributed to an automatic technique that aids developers of novel first-order quantified axiomatizations, such as the ones that are used to power the techniques of my thesis. Next, I will explain at what level of the verification tool stack do the core contributions of my thesis come into play. At the top of the stack is, of course, the programmer, who writes the program implementation together with its formal specifications and submits it to a front-end verifier. This is a lightweight tool that encodes the input program into separation logic and sends it to the Viper system. In turn, Viper uses the Z3 SMT solver to automate its reasoning steps. Each verification attempt produces certain results that are lifted by the front end back to the level of the source program and reports them to the programmer. The reasoning techniques of my thesis mostly contribute at the level of encoding, but also at the level of specification language design, because ultimately the expressiveness of a specification language determines the overall generality of the verification technique. On the opposite side of the pipeline are the contributions of the verification debugging technique. In a scenario in which verification fails, the SMT solver produces a low-level model. This information is used by the verification debugger in order to generate a counterexample heap model that the programmer can understand. In the remainder of this talk, we will discuss the reasoning techniques on the left side of the pipeline. So let's proceed with the first technique. This is a technique for reasoning about comprehensions. So first of all, what are data structure comprehensions? To illustrate, consider a simple program that iterates through the elements of an array, summing up their values and storing the sum in a variable called s. To verify this program, we need a suitable loop invariant, such as this one. Here we use the common big sigma notation to express that the variable s indeed contains the sum of the array values that we've seen so far. While simple, this formula is powerful enough to summarize a potentially unbounded array. Here is a slightly more involved example, which you do not need to understand in full detail. This is a minimal subarray sum program, and it offers an optimal solution to the problem of computing the sum of the minimal subarray of a given array. For our input for our example array here, for instance, the answer is -8, corresponding to the subarray which is highlighted in green. The loop invariant that is required to verify this program is well known from the literature and has the following form. Notice that it involves two different types of comprehensions, namely minimization as well as summation. Next, let's discuss the problem of automated reasoning with comprehensions, and in particular, how would we approach automatically verifying the loop invariant for minimal subarray sum? We represent this problem as a Hoare triple, focusing on the body of our loop, and at the top we have the condition that the invariant holds in the state of the beginning of some loop iteration, whereas at the very bottom we have the condition that the same invariant holds at the end of the same loop iteration. The actual proof outline for this Hoare triple is too big for one slide. However, it involves the following kinds of reasoning steps, such as linear arithmetic, as well as weakest precondition in order to reason about our assignment statements. However, it also involves the property of distributivity of plus over minimization, as well as the so-called decomposition property of comprehensions. These two, highlighted in red, are examples of higher order properties. The higher order nature of comprehensions is exactly what makes it hard to automatically reason about them. But before I present how my technique addresses the challenge of automated reasoning, let me first introduce the formal notation that is used by the technique. In this technique, comprehensions consist of 4 parts. N of type t is called the iterated variable of this comprehension. And the red part, called the body of the comprehension, is a state-dependent expression over the iterated variable. And the yellow part is called the filter of this comprehension, and it determines which instantiations of the body expression to consider. Finally, the blue part is called the semigroup, and effectively this gives us a binary commutative associative operator that allows reducing a set of values of some type S to a single value of the same type. Here is an example that connects the common mathematical notation with our notation. In this example, we express minimization of the values stored in the val field of objects in the node set. And here's how we can do it in our notation. how do we encode this notation into separation logic? To do so, we replace each comprehension in our notation with an application of an uninterpreted function called comp. This function takes two arguments. The first argument is called the snapshot, and it encodes the body of the comprehension. The second argument is called the filter set, and it encodes the filter. Here is an example. Given a comprehension that sums up the elements in an array, our technique translates this comprehension to the application of comp over some b and some f. And for a concrete array that consists of only 3 elements, namely -1, 1, and 5, the technique would generate the filter set as the set of indices of this array, namely 0, 1, and 2, while the snapshot would map these indices to the corresponding values stored in the array. We're now ready to return to the general problem of automatic reasoning with the comp function. The key idea in our technique to automate reasoning with comp is that since comp is an uninterpreted function, we can write first-order axioms that express its properties. For example, our technique produces the following axiom that defines the value of comp over a singleton filter set. It defines it as the corresponding lookup into the snapshot map. Our technique also emits a number of other important axioms, and together these are expressive enough to enable automatic reasoning about a diverse set of benchmarks, including those from closest related prior work. Next, let's talk about the problem of modular reasoning with comprehensions. To support modularity, our technique needs to encode the first 2 arguments of the comp function, and to do so, we employ 2 new functions called snap and filt. The encoding of this technique works under the following key assumption, namely that each method specifies its footprint explicitly as a set of references to memory locations. And in separation logic, this footprint can be specified using the big star notation. Fortunately, automated reasoning with the big star is enabled by recent advances in automatic verification. Here's an example that shows how our encoding works in practice. Say we have a comprehension that iterates over references R, summarizing their values in the val field for all such references within the current footprint G. It doesn't matter what the semigroup is in this case, but our technique would encode this comprehension as an application of comp over snap of G and filt of G. In this simple example, filt of G is simply G itself. However, to encode the semantics of snap, our technique would emit the following formula. Here, we define the values stored in the snapshot map at an index R as simply the evaluation of the body expression of our comprehension. Notice that the left-hand side of the implication guarantees that the body expression can be only evaluated for appropriate values of R within the current method's footprint. Generalizing this idea, of course, comprehensions can use iterated variables of arbitrary types, and therefore our technique lifts the requirement in the left-hand side. However, conceptually it still requires that the body expression is evaluated only for those values of the index n that identify objects within the current footprint. The details of this encoding are presented in the second chapter of my thesis. And next we evaluate this technique, and to do so we consider a number of benchmarks which cover two categories of data structures, namely arrays as well as graphs. And the closest related work to ours is a technique proposed by Leno and Monahan for the spec-sharp system. Their technique requires that comprehensions specify ordered data structures such as arrays. In contrast, our technique lifts this limitation. An additional novelty is that we encode our technique in separation logic, which enables for modular reasoning. Now, let's proceed with the discussion of the second technique. This is the technique for reasoning with local reachability. Recall that in separation logic, we specify properties of the local method, which correspond to its footprint. Therefore, the notion of classical or global heap reachability is not very useful here. To illustrate the notion of local reachability, here is a concrete heap configuration in which horizontal edges correspond to the F fields of nodes, while vertical edges correspond to the H fields. For example, you can see that v.f.h equals u. Therefore, we learn the local path predicate that connects v to u. Additionally, we can see that u.f.f equals w. Therefore, we can learn that there exists a local path from u to w. However, local path predicates allow defining paths of arbitrary length, even if they're unbounded. Therefore, in the following, we will abstract away from the concrete heap edges and represent paths of arbitrary length using wavy arrows. Here's another example fact that we can learn in this configuration. There does not exist a glocal path that connects u to v. Although there does exist such a path in the global heap, in order to reach v from u, one would need to first exit the local footprint g. And finally, due to transitivity of local reachability, we also learn that there exists a glocal path from v to w. So what are the use cases for local reachability? One such use case is to specify acyclic structures. In particular, here's a formula that shows how local path predicates can be used to define that part of the heap denoted G represents an acyclic structure. Other important use cases for local reachability include properties such as disjointness and heap cycles. You can see that these are foundational properties that are essential for specifying heap allocated data structures. Next, let's discuss how we encode local reachability into separation logic. Here, we reuse the idea that I presented for the first technique in this talk. Namely, we replace local path predicates with an application of an uninterpreted predicate, which is called P. And we axiomatize the properties of P in first-order logic. The first argument is a set of edges which represents the current footprint in a particular state, and the second and the third arguments represent the beginning and the end of a heap path. Our encoding works under the same assumptions as in the first technique. And in order to obtain the first argument for our predicate P, the technique relies on a function which is called rsnap. What rsnap does, in effect, is it takes the current method's footprint and yields the set of edges which represent this footprint in the current state. Here is an example. Given this data structure, say that the current footprint is comprised of its middle part. In this scenario, our snap of G is going to contain all heap edges that originate inside G, and we denote these in orange color on the diagram. Here is a simplified version of the general formula that represents the semantics of our snap in our technique. And the details of this encoding are presented in the third chapter of my thesis. However, there is a fundamental difference between the comprehensions technique and the technique for reasoning with local reachability that we're discussing here. And the problem is that not all essential properties that we need can actually be represented in first-order logic. To illustrate the problem, consider the following scenario. Here, we consider a case in which x and y are two nodes within the footprint of the call, and we are to show that there does not exist a client local path from x to y. In order to do so, we would need to consider potentially multiple cases. In the first case, the shape of the path fits entirely within the footprint, and therefore there is only one footprint local path predicate that is required to express this situation. However, if we don't have enough information to satisfy this condition, then we would need to consider another case in which our path from x to y has a more complex shape. Therefore, we would need to consider a combination of three local path predicates to describe this situation, because the footprint local path from x to a exits the footprint, and then we have a frame local subpath from a to b that reaches the footprint again, and finally the third segment is a footprint local path from b to y. However, again, if we don't have enough information to satisfy this condition, then we would need to consider yet another situation in which the shape of the path is even more complex. In this case, the situation leads to the combination of as many as 5 local path predicates that describe the situation. As you can see, this can go on, and the number of cases that we would potentially need to consider is not bounded. And this is exactly what makes it hard to reason about reachability automatically. What we're looking for is a viable simplification of our setting that on the one hand would support common data structures, and on the other hand would enable a technique that can be automated using common SMT solvers. In the course of my thesis, I have identified such a simplification. This is called relative convexity. So intuitively, a footprint is relatively convex in its client's footprint if by following a path that starts in the footprint and exits it, one cannot return back into the footprint. In particular, this avoids the problematic configurations that we've just experienced. And therefore, we can reduce an unbounded case analysis to an analysis of a finite number of cases, which is a prerequisite of an automated technique. Another advantage is that relative convexity supports a technique that is fully precise, which means that by applying the rules of our technique, reachability information cannot be lost. Another important aspect is that the restriction of relative convexity itself can be checked automatically. and this is again important for an automated technique. And finally, this restriction is weak enough such that even heap structures that contain cycles are permitted. Next, I will emphasize the very first of these points and explain how exactly do we reduce an unbounded case analysis to an analysis of a finite number of cases. To do so, we will consider the problem of converting client local reachability information into a combination of only footprint local and frame local reachability. And again, we have to consider the following cases. The first case is that x and y both fall into the footprint of a method call, and therefore a client local path from x to y cannot have the following shape, because that would violate our assumption that the footprint is relatively convex. As a result, we can represent the existence of this client local path from x to y using a single footprint local path predicate. In the second case, x falls into the frame and y falls into the footprint. And again, due to relative convexity, we only need two local path predicates, one frame local and one footprint local, in order to represent the client local path from x to y. Notice that the shape of this path cannot be more complex than this, because otherwise we would violate our assumption that the footprint is relatively convex. The third case is analogous to the second one, and here again we need a combination of two local path predicates to represent our client local path that starts in the footprint and ends in the frame. Most interesting is the final scenario in which both x and y fall into the frame. Two possibilities arise here. One possibility is that this entire path remains within the frame, and alternatively, it crosses the footprint, but it can do so only once. And again, this is due to relative convexity. So even in this scenario, the client local path from x to y can be represented using a combination of a finite number of frame local and footprint local path predicates. Overall, we can see that there's a finite number of cases that one would need to consider in order to perform a conversion of our original client local path. Therefore, we're reducing an unbounded case analysis to an analysis of a bounded number of cases. And this is a prerequisite of an automated technique. To give you an idea about the expressiveness of the technique, here are the categories of supported structures. So the first such category is directed acyclic graphs with a finite out degree, and our technique supports a rich spectrum of relatively convex decompositions of these. In addition, the technique also supports the class which is called the 0-1 path graphs. These are structures in which between any pair of nodes there exists a unique path modulo cycles. So these potentially cyclic structures are also supported together with a rich spectrum of their relative convex decompositions. How does this compare to the state of the art? Sakarizaki et al. Proposed a technique for modular reasoning about the global reachability relation. The emphasis of their work is on decidable fragments of first-order logic, and in particular, this reduces the supported data structures to various forms of linked lists. Grasshopper is the first tool for reasoning about reachability in separation logic. But this tool supports trees and linked list structures. In contrast, our technique supports all categories of structures listed on this slide. enabling many new ones that are important in practice. To summarize this talk, I've presented to you today two techniques for compositional reasoning in separation logic. The first of these techniques enables reasoning with data summarization properties, namely data structure comprehensions. And the second technique enriches the specification language with shape-defining local reachability predicates. Thank you for your attention.